I'd like to dedicate my talk to Cecilia Payne, which is, I think women are a little underrepresented, sometimes under-recognized in astronomy. But she's the person that discovered that the universe was mostly hydrogen. And she has this beautiful quote, which we'll take the time to read. So looking back on my years of research, I don't like to dwell only on my mistakes. I'm inclined to count my blessings, and the two seem to me very especially valuable. The first blessing is that the process of discovery is gradual, and if we were confronted with all the facts at once, we should be so bewildered that we would not know how to interpret them. The second blessing is that we are not immortal. I say this because, after all, the human mind is not pliable enough to adapt to the continual change in scientific ideas and techniques. I suspect that there are still many astronomers who are working on problems and with equipment that are many years out of date. Now that I am old, I see that it is dangerous to be too much in a hurry, to be too anxious, to see the final result for oneself. Our research does not belong to us, to our institution, or to our country. It belongs to mankind. Now, I'm a great admirer of Cecilia Payne, and she actually wrote many beautiful papers in her time. She was also the chair of astronomy at Harvard, for those who don't know, and that was quite a few years ago. So just a great person in astronomy, a wonderful human being. So the first thing we'll talk about is, just very briefly, the gaseous models of the sun and the stars. You know, we're taught as children, well, the sun's a gaseous plasma, and we think, well, this is really a modern idea, you know, but actually it goes way, way back. The sun became a gas actually in 1864, and I've mentioned this before for those who have seen some of my talks on YouTube. And the person who came up with that was actually an evolutionist, Herbert Spencer, who's under-recognized in astronomy, but he said that the sun was a ball of gas, and it contained a liquid photosphere or solid photosphere or condensed matter photosphere enclosing. So he kind of had like a balloon idea containing gas inside. But the sun really became a gas through Father Angelo Secchi. He saw it as a gas with floating condensed matter, solid materials floating on the photosphere. And Hervé Faye, at the same time in 1864, came out with papers, 1864, 1865. Immediately following Secchi, Faye came up with similar ideas. And, you know, we say in the gas model, well, the sun doesn't have a surface. And people think, well, that's really, you know, our mathematics or whatever, our modern ideas tell us that it can't have a real surface, but actually the idea is really old. It was in 1865 that the sun lost its surface, and that was by Hervé Faye. So I think it's time for a change. So anyhow, it says Hervé Faye in 1965, and I translated this, so if it's not perfect, you can go to the French and get a better translation. But so then the exterior surface of the sun, from which from far appears so perfectly spherical, is no longer a layered surface in the mathematical sense of the word. The surfaces, roughly made up of layers, correspond to a state of equilibrium that does not exist in the sun. This limit, in any case, is only apparent. So the surface of the sun became an apparent thing, and this is still how solar physicists see it today, that the sun doesn't have a surface. This is just an optical illusion. It's caused by a change in opacity that causes us to perceive a surface there that is not real. And this goes back, this is not a new idea, even though they're advocating it as something fancy. And in 1865, when Faye said this, of course, what did they have to establish, did the sun have a surface or not? Of course, many observational astronomers at the time actually believed it did have a real surface. At the same time as Faye, Secchi, and Spencer were writing, again in 1865, Warren de la Rue, Balfour Stewart, which for those who know me know that he's one of the people that I have really admired a lot, and Benjamin Lowry, they wrote a paper, and they proposed that the continuous spectrum of the sun was consistent with a fully gaseous sphere. So as you know, the sun emits in white light, And they said, well, the gas can do that. And this is a quote from their paper. From all this, it was inferred that the luminous photosphere is not to be viewed as composed of a heavy solid or liquid matter, but rather is either of the nature of a gas or a cloud. And then Frankland and Lockyer, now Lockyer was the founder of the journal Nature, they wrote, the gaseous condition of the photosphere is quite consistent with the continuous spectrum. The possibility of this condition has been suggested by De La Rue, Stewart, and Lowry. Now, of course, this was false. A gas cannot give us a continuous spectrum. But today, we still argue that the sun can give us a continuous spectrum even if it's a gas. And these ideas go back to 1865. Now, all our physical knowledge since that time has demonstrated that this is not possible. Yet, we still prevail in saying the sun can give us a continuous spectrum even though it's a gas. And how do we do that? The way that they do it is they say, well, look, we have inside the sun, we have a lot of atoms, and they're in different states of ionization. And through all the sum of many processes, all these processes that we're going to add together, they'll give us that continuous spectrum, like magic. But everywhere else in spectroscopy, and I'm a spectroscopist by training, if you have a certain type of spectrum, you have a distinct process that produced it. So we get an NMR line because we take spins, we put it in a magnetic field, we cause the transitions, and we get these lines. If we get a Balmer series, we must have hydrogen. So every spectroscopic process that occurs in nature has a specific thing that produces it. Now, graphite produces for us the continuous spectrum. And the process that produces that in graphite, and surprisingly, even though we're chasing black holes and big bangs, we still don't understand why it is that graphite produces a continuous spectrum. And this is actually a central problem for humanity, to more closely understand why it is that we get a continuous spectrum from condensed matter. So we spend our money, we invest a lot of money in chasing things outside the Earth. Now we're going to chase aliens, unfortunately. But instead of doing this, we should spend our money supporting scientists that are doing not very fancy research, just very ordinary guys that can explain for us why it is that graphite produces a continuous spectrum. And the reason this is so important is that once you understand why graphite produces a continuous spectrum, then the sun will be bound by the same mechanism. And that will also be true for any other continuous spectrum that you get in nature. So this is an extremely important point, that great discoveries in science don't occur because we spend a lot of money chasing things that seem fanciful. They occur because some quiet scientist somewhere that everyone has ignored has been in the lab working, and that person made a discovery which led to new understanding. Now, Henry Norris Russell, who is part of the HR diagram, when you talk about the HR diagram, the R in the HR diagram, which describes the mass luminosity of the stars, Norris Russell wrote on why do we have in his book, which is cited here at the bottom, why do we have a fully gaseous sun? And he writes in section 572, formerly the photosphere was supposed to consist of solid or liquid material, but various lines of evidence now prove that it, and indeed the whole sun, is gaseous. This is in 1927. The solar atmosphere is necessarily gaseous since the pressures prevailing are known to be very low at these temperatures, except perhaps the last, there he talks about the corona at 3000, are above the temperature of volatility of even the most refractory known materials, such as carbon and tungsten. Thus, the important conclusion is indicated that the solar atmosphere, with the possible exception of the outer reaches of the corona, no known substance can permanently exist except in the gaseous state. And of course, this is because we have critical temperatures, and it was known that the critical temperature of even hydrogen is extremely low. I think it's like 33 Kelvin. And so you can't pressurize hydrogen at high temperatures just because you can't pressurize hydrogen enough, if the temperatures are high, that it'll become liquid. And of course, when these people wrote this, they didn't realize that metallic hydrogen would exist, and that will have a different critical temperature, and so it could be a liquid at much higher temperatures and pressures. So basically, these statements are completely out of date. But if you ask an astronomer, why is the sun a gas? Just ask them, why is the sun a gas? It's a very simple question. And they actually will not be able to answer the question except to say, well, it's too hot to be anything but a gas. That answer from 1827 is still what we learn today. And I had the privilege of sitting in on some graduate astronomy courses on the sun, and it was interesting. The phase of the sun was never discussed. Why is the sun a gas? It's just the sun is a gas, and now let's do the mathematics of a gas for an entire semester. So first you got to get the phase right, then let's worry about the mathematics. The sun is viewed as the Rosetta Stone of astronomy. If you get the sun wrong, you'll get all of astronomy wrong. So it's extremely important that we set the phase of the sun correctly. Accepting a new phase for the sun will lead to the collapse of modern astronomy. So if you say that the sun is a liquid, astronomy will collapse. Well, some people say, well, this is a terrible thing. But actually, I think it's good for our children. It will give them some work in the future. And I think that's a problem with science when everybody likes accolades, but I think it's much better not to be too well known. And the reason is because when you put somebody on a pedestal, they tend to stay there. And that's a very dangerous thing, because then our children cannot take them off the pedestal. So don't put people on pedestals. It's too dangerous. Each star type, stellar evolution, and galactic formation has to be revisited. A liquid sun would be essentially incompressible by definition. So that means stars cannot collapse into black holes at the end of their lives. Stars don't collapse. Big Bang cosmology will be confronted with limits to maximal densities. So if the sun can't collapse, how do the stars collapse? How do you get material into nothing? There's also a problem for Eddington's proof of general relativity, because remember, and the citation is there, for Eddington, the corona could be treated as a vacuum. He had to have it as a vacuum. So we have densities there of 10 to the minus 15 grams per centimeter cube, which is, believe me, a very, very powerful vacuum. So remember that the proof of general relativity is that during an eclipse, the light of distant stars as they crossed near the sun was bent, and this became the first great proof of general relativity. But the problem is, if there's actually density in the atmosphere of the sun, in the corona, you'll have diffraction. And so then you don't have a proof of general relativity. So this has consequences when you change the phase of the sun. It's much more than just changing how all the stars are. Now, I've wrote a paper, got carried away, 40 lines of evidence that the sun is condensed matter. But actually, there's only one proof that we need. And this proof we've had since the days of Langley, when he first measured the continuous spectrum of the sun. And as I mentioned before, in order to have a continuous spectrum like this, the sun must be condensed matter. You cannot get it from a gas, and I've treated this in detail in this paper, Stellar Opacity, the Achilles heel of the gaseous sun. So you cannot take a whole bunch of non-thermal processes, just random spectroscopic processes, take an infinite sum, or not an infinite sum, take a sum, a large sum, and then create this spectrum at every layer inside the sun, and until finally you get it on the photosphere. That requires that whatever soup you're building changes constantly within the sun to have the right properties so that it can change the spectrum with temperature. It just doesn't work. So we have Roslin mean opacities, which the solar physicists use to treat this problem, and it's just an excuse for not understanding a process. So you can't do it with a gas, and that's the critical point. Now, there's problems with it. My son is in Scotland right now. He's doing a master's in brewing and distilling. And, but Luke has been a great pillar in my life. And, but he wasn't able to help me with my figures as he normally has done ever since he was a child. He's a phenomenal artist. Actually, he has a little YouTube channel, and you could see him drawing cards and stuff. He's really good. But anyhow, he normally draws my figures, and I had to draw this one myself because he was in Scotland. So, but in the gaseous model, you see that the core has a temperature of about 16 million degrees. And then the photosphere, they tell us, is 5,000. Then the chromosphere is 3,800 to 25,000 about. And then in the corona, now you've got temperatures of millions of degrees, right? 2 million degrees, even 10 to the 8th, 10 to the 10th Kelvin. Now, how does this make sense? And that's because they're seeing these free atoms in the corona, and they're ascribing, okay, to remove that many electrons into free space, if I had to bombard something and remove that many electrons, I would have to have these unbelievable temperatures. And of course, we all know that, you know, if you want to remove electrons from something, all it takes is to have a material that has a higher affinity for the electrons. Now, Planck actually commented on the continuous spectrum of the sun. I'm sorry if I'm going slow. I might go a little over, but hopefully you bear with me. Now, Planck commented on the, I took out 15 slides, by the way, because it's already too long. So Planck commented on the solar spectrum years ago, and people don't, you know, Planck has done a lot in science, and people, they quote scientists when they want, and they decide not to quote them when they don't like what they had to say. But here, Planck says something to the solar physicists of still today. He says, now the apparent temperature of the sun is obviously nothing but the temperature of the solar rays. Now he's talking about the continuous spectrum. Depending entirely on the nature of the rays, and hence a property of the rays, and not of a property of the sun itself. So he's telling you, this is not a property of the sun here. Therefore, it would be not only more convenient, but also more correct to apply this notation directly, instead of speaking of a fictitious temperature of the sun, which can be made to have meaning only by the introduction of an assumption that does not hold in reality. So Planck knows that in order to get a valid temperature, you have to follow the laws of emission. And those laws require certain things. You can't have convection. You can't have conduction. Now, is there convection on the sun? Well, clearly there is. Carrington showed us that there was convection a long time ago, right? We see the sunspots going around. The sun has convection currents. So that forbids you from taking a temperature. So that's against the laws of emission. You have to have enclosure, thermal equilibrium with a rigid enclosure. The sun never meets that requirement. So that's why the 5,000 degrees has nothing to do with the actual amount of energy that's sitting at the photosphere. It's much, much higher. So what is this 5,000 degrees actually representing? And what I've tried to tell people, and you can come up with your explanations, but what I've tried to tell people is it's linked to the vibrational degrees of freedom of the lattice of the sun, that the sun has a real lattice, it's hexagonal planar, as you'll see later, and it's the energy that's contained within that lattice that's expressed in this temperature. So setting a temperature for the sun, the surface of the sun does not meet a requirement for a black body, which is rigid enclosure with no conduction or convection currents. The sun maintains energies in conduction bands and convection currents. As a result, it can never produce a genuine black body spectrum. The spectrum has a thermal appearance, but provides only an apparent temperature of 5,800 Kelvin. The spectrum is linked to vibrational energies, degrees of freedom of the photospheric lattice, and the sun's surface can produce X-rays. We know this. We can get X-rays off the sun, and that would require temperatures in the millions of degrees. Again, you could read the paper on stellar opacity. So now there's another problem, is setting a lower temperature for the umbra and penumbra ignores the fact that materials which are more metallic have both lower normal emissivities and increased ability to support magnetic fields. So what does this mean? You know, when we're looking at a sunspot, it looks darker to us. And for years, they've been telling us, well, that's because the temperature is lower there. But that's not what's happening. The sunspot's more metallic, and something that's more metallic has lower normal emissivity. Normal emissivity means if I look at the plane of the material, it's normal to the plane. So when I look straight down on the material, I'm looking at it normal. Okay? So if I look at the normal, the emissivity is lower in a metal. It's higher in a non-metal. So the photosphere is less metallic than a sunspot. We know that. Sunspots have magnetic fields inside of them, right? So strong magnetic fields. So the sunspot is more metallic, therefore its emissivity is lower. It has nothing to do with temperature. Very little to do with temperature. Most of the effect has to do with the structure of the spot itself, the lattice structure of the spot. So I said that the sun is made up of a hexagonal lattice of hydrogen that's planar. And in the sunspot, that lattice is a little more compressed, and therefore it's more conductive. So you get more conduction, and therefore the emissivity drops. So the sunspot looks darker, but it's not any colder, which doesn't make sense to say that it was colder, because they're trying to tell us that the sun has a temperature in the millions of degrees. Okay, and now we have an infinite, or not an infinite, a very little thin layer, the photosphere, and it's at 5,000 degrees. And then just right near the photosphere, now we got sunspots at 3,800 degrees, next to millions of degrees. So this doesn't make any sense. These temperatures don't make any sense. And I think this is the beauty of the public becoming interested in science. And I think there again, Ben has a lot of people can thank Ben for trying to bring science more to the public. That the public needs to say, well, look, guys, we can't take this anymore. We're fed up. Science will change when actually the population says, we don't believe you guys anymore. Okay. So assigning coronal temperatures in the millions of degrees using line spectra of isolated atoms necessitates the dismissal of attributing the continual spectrum of the corona to the corona itself. So the corona has a spectrum, it's continuous, but they say, well, this spectrum comes from reflection from the photosphere. It's being reflected. It's a photospheric spectrum that's reflected out here. It didn't produce a spectrum out here. Why don't they want to produce it there? Because in the gas model, they have no means of producing the spectrum there. But in the condensed matter model, we say there's condensed matter in the corona. Why do we say that? Because we see the sun emitting it, right? We see coronal mass ejections. We see condensed matter being propelled into the corona. There's material there. It's condensed, and it can give us a continuous spectrum, okay? By itself. It doesn't need to reflect a photospheric spectrum. So they have to produce these ions by high temperatures. Now, that ignores data from the 1920s or before that showed that the coronal continuous spectrum was reddening as you moved away from the surface of the sun. So if the corona is reddening, if that continual spectrum is becoming more cool by going to the red, that means that it can't just be reflecting photospheric light. It has to be its own, because the photospheric light is just being scattered, right? You have no mechanism to redden it. So they don't talk to us about the fact that the coronal spectrum is reddening as you move away from the surface, okay? So, but that's important to remember that this was shown even in the 1920s. So flares, coronal mass ejections, also produce their own continuous spectra, which are not at millions of degrees. So current methods require numerous means to heat the corona. Actually, this is a real problem for the gas model, right? They have the photosphere at 5,000 degrees, and then they have to bring the corona up to millions of degrees. Well, how do they do that? They have to heat it. So they have all these mechanisms to heat the corona. And of course, what I'm saying is, look, guys, it's actually not hot. It's actually cooler than the photosphere. But the material that's there has very high electron affinity. It wants the electrons from those free atoms and strips the atoms of their electrons. That's why you get iron 25. It's not because the temperature is high. It's just that you've put something in contact with something that really wants electrons. Well, it's going to strip it of its electrons. It's not complicated once you put condensed matter there. So once you put condensed matter, you can easily explain these lines. Now, I like this slide because this slide, you know, for people who can't understand the continuous spectrum and all the physics of, you know, how do you get a continuous spectrum and spectroscopy, and they're not interested in this, and it's all foreign to them. But this one is so easy, right? So if this is a flare, it's a Doppler image of a flare. So the white that you see here is a flare that's coming out of the surface of the sun. And as it breaks the surface of the sun, you see these ripples that are going out. Now, in the paper, they actually talked about this resembles ripples on a pond. Well, ripples on a pond are transverse waves, right? Now, you only get transverse waves in condensed matter. So once you have a transverse wave, gases can only sustain longitudinal waves. So this image is enough, as a child can easily tell us the sun is not a gas once you see this image. So I cited this image when I took an ad in the Times, for which I got a lot of flack. And I want to thank my wife today, who's sitting in the audience. It's rare. It's the first time my wife's at one of my talks. So now, of course, I wouldn't have done anything in life without my wife. I would never have been a scientist. We've been married 35 years. So I was 19 when we got married, and she made somebody of me. But, well, I don't know if I'm somebody, but she did a lot for me. But in 2002, I had a friend who was well-positioned in science, and he had trained with a Nobel Prize winner, and I had told him the sun was a liquid, and he said, Pierre, you will never say it. No one will ever let you say that the sun is not a gas. And I said, well, what do I do? And he said, well, Pierre, just say it in the New York Times. And I was like, oh, come on, you can't be serious. I'm not going to say the sun is not a gas in the Times. He says, oh, yeah, just say it in the Times. He said, the only thing that matters is that you say it, and that people must know you say it. And that, in the end, you know, we're all our peer reviewers, right? Everybody has to think about science. It's everyone's responsibility. So I did take the ad in the Times. It cost us $100,000, which was everything we had at the time, and we had little children. So I did want to thank my wife for that today. So I was going to talk about Kirchhoff's law because actually you can't really understand the sun without dealing with the problem of Kirchhoff. But the problem is that there is limited time, so I spared you for most of it and dropped most of these slides. But for those who are interested, I gave a talk at the EU, and I see David Talbot there back in the back of the room. I gave a talk at the Electric Universe last year, and they had a fantastic video presentation, and you'll see my talk soon on Kirchhoff's law appearing on YouTube. But it's important to remember that a proper understanding of black body radiation is important, as it touches virtually all aspects of physics, from the study of condensed matter to the understanding of noise power and MRI, which got me into this mess in the first place, to fundamental astronomy, to setting the temperatures of the sun using thermal spectra. So it's extremely important. This law is old, and it has huge implications in physics. But the problem is that the law is not valid. It has no experimental proof. When Kirchhoff wrote the paper, it was all theoretical. There was no theoretical proof of what he was, there was no experimental proof of what he was saying. But a law of physics can only come from experimental proof. Kirchhoff had none. Such proof doesn't exist today. But a further problem for physics is that the theoretical proofs are invalid. There are no theoretical proofs of Kirchhoff's law. So last year, along with Steve Crothers, we went over Planck's proof of Kirchhoff's law, and we discovered that to arrive at Kirchhoff's law, Max Planck inferred that the reflectivities of two arbitrary materials were equal. So if you look at his book, which is cited here below, his equation 40 is that the reflectivity of one arbitrary material is equal to the reflectivity of another. And that's a complete violation of all of known physics. The reason that we see colors is because reflectivities are not equal. They're never equal. The reflectivities of two arbitrary materials are never equal. So Planck could never properly arrive at this equation. But nobody caught him on it. This equation has been sitting in an important physics book for 100 years. Everyone can understand it, right? It's just A equals A prime. It's the same thing, or R equals R prime. These two reflectivities of two arbitrary materials are equal. Planck tells us the reflectivities of all arbitrary materials are equal. That's a violation of all of known physics. Now, in Planck's world, what does this mean? In Planck's world, there are no colors. So this is where physics has taken us to this date. Because of Kirchhoff's law, Planck's equation has never been linked to the physical world. It's a little complicated to understand, but every equation in physics has to be linked to an underlying mechanism. There has to be a physical cause. But Planck was never able to link his equation because, according to Kirchhoff, the means of generating the black body spectrum was independent of the nature of the walls. It didn't matter what the box was made out of. So Planck was never able to make a link. And this is a huge reason why astronomy is so messed up today. You know, people are looking for all kinds of things of trying to explain why there's no big bangs or whatever. Don't look there. Look for simple things like this. Planck's violation of the laws of reflectivity. And then also the fact that Kirchhoff tried to tell us that without experiment, that his law was valid. How do you make a law of physics without any experiments to prove it? So remember, whatever mechanism is eventually used to account for graphite, for the black body spectrum in graphite, must be present in the solar spectrum. So however graphite does it, the sun does it. That is why a gaseous sun cannot survive if Kirchhoff's law is found to be invalid and if Planck's equation is finally linked to the physical world. So link Planck and then Kirchhoff's law, the sun, the gaseous sun, will collapse. In the end, Kirchhoff's law of thermal emission is not valid as it has no experimental or theoretical proof. As a result, the foundation of the gaseous sun collapses. And that's why I've spent so many years on Kirchhoff's law, people wondering, why does he care so much about a law of 1859? And that's the reason, because now let's say, just look at your own lives. If there was a law that said, well, if you're British and you come and drive in the United States, you're not allowed to drive on the right. You must drive on the left. That would not be a good law, right? So the same thing here with Kirchhoff's law. What happens when a law of physics is not correct? And we have built all of modern physics upon it. That's a problem. Now I'll review a little bit of the liquid metallic hydrogen model of the sun. So our sun has confronted, this is a quote from my paper, it has confronted humanity with an overwhelming evidence that it is comprised of condensed matter. And in the paper I divide it into different types of proofs. There's Planckian proofs, there's structural ones, there's helioseismic proofs. We do seismology on the sun. Now if you do seismology, you do that in condensed matter. You don't do that in a vacuum. Okay? We have spectroscopic lines of evidence, there's dynamic, elemental, and there's even some unearthly proof. So there, long before me, the idea that the sun was a liquid was advanced by others. And the most important of those was Kirchhoff himself. Kirchhoff thought the sun was a liquid. He thought the photosphere was either a liquid or a solid. It had to be condensed matter. It could not be a gas for him. Why? Because of the continuous spectrum. So he saw that the sun had a continuous spectrum. He said, okay, that's a liquid or a solid. It can't be a gas. But then he built a law that enabled astronomy to say, well, no, a gas can produce that spectrum. It's because of Kirchhoff's law that a gaseous sun appeared. So he knew the sun was a liquid, and then he built a law which enabled astronomy to say it could be a gas. Lord Kelvin, and if you want to read about this, I think the papers on the history of the sun that I wrote years ago, they're a fun read, and you'll learn a lot about this old history, and I think it's important that we understand the historical context of where we are today. And of course, the most important one was Jeans, and Jeans was, he became the head of the secretary of the Royal Society in England, so he's not just a nobody, and he felt that all the stars were liquids. One guy that's interesting is Charles Hastings, and the reason is that he felt that the sun was a liquid, but from the carbon group. There was something he wanted to tie it to carbon. This is what he wrote: granting this, and this is in 1881, granting this, we perceive that the photosphere contains solid or liquid particles hotter than carbon vapor, and consequently not carbon. At any rate, we are sure that the substance in question, so far as we know it, has properties similar to the carbon group. So he's looking for something that's going to behave like carbon, but it's not carbon. In 1881, so he had great insight, and he knew this from the spectrum of the sun. And you'll see later, I'll discuss this again. Now, Jeans, he had wanted the sun to be made from uranium or radium. So he wanted fission, and he thought, well, if I make it from uranium or radium, I could drive the energy from that. So in brief, every rotating body conducts itself either as if it was a pure liquid or as if it was a pure gas. There are no intermediate alternatives. No other mechanism, so far as we know, is available for the formation of the numerous spectroscopic binary systems. In these stars, then, the central condensation of mass must be below the critical amount just mentioned. To this extent, they behave like liquids rather than gases. So he was a great advocate for liquid stars, and eventually, though, Menzel, I think it was, Payne discovered that the universe was a liquid, but I think Menzel, who worked on the chromosphere, is the one that really established that the sun was made out of hydrogen primarily. And so Jeans lost his building block. He couldn't have he thought, well, there's no way that I can get a liquid sun from hydrogen. And so he abandoned it. And he had a textbook, and up to the 3rd edition, it was always liquid stars. And interestingly, in the 4th edition, he abandons liquid stars, but never tells us why. And that's, I comment on that, and it's an interesting story of how Jeans changed his mind without telling anyone. The sun is condensed matter and has a true surface. And in order to, this is the things that I've been saying, solar emissivity must be accounted for by the presence of a structural lattice. So the sun not only is, when I say condensed matter, it's not a loose thing. We have to have an actual lattice structure on the sun. That's extremely important in order to get its emission spectrum. And so this is the lattice structure that is proposed, that it's a hexagonal planar structure, and this is, the little balls there are all representing hydrogen atoms. Now you'll recognize that if you're a chemist, that that's the same structure as graphite has, right? So this is the same structure as graphite. So we look at Hastings, he wanted the carbon group. In 1881, he wanted something that behaved like carbon, okay? Because he knew that that's the spectrum he wanted, and the hydrogen, of course, here is going to be in the same structure, and it should be able to give us the same spectrum. So in organic chemistry, and I was a chemist by training, the organic chemists know that carbon, the little cousin of carbon, is hydrogen. And Wigner and Huntington, when they proposed metallic hydrogen so they're talking about hydrogen in this paper. In 1935, they proposed that metallic hydrogen exists. Now, that's too bad for Jeans. If he had seen this paper, he wouldn't have abandoned his liquid stars in the 30s, okay? He could have gone back to them, but he probably was unaware of Wigner's paper. So the objection naturally comes up that we have calculated the energy of a body-centered metallic lattice only, and that other metallic lattices may be much more stable. We feel that the objection is justified. It is possible, however, that a layered lattice such as has much greater heat of formation and is obtainable under high pressure. Diamond is a valence lattice, but graphite is a layered lattice. So here they're telling us, okay, metallic hydrogen could adopt the structure of graphite. Now, Neil Ashcroft, who's an eminent physicist in the United States, he wrote a paper on comparing graphite with some metallic hydrogen with graphite, and this is what he wrote. On a little reflection, it is apparent that all the qualities remarked, just presented on the band overlap state in dense hydrogen, could also have been made with minor modifications about graphite, a trivalent, hexagonal, band overlap, 1 atmosphere semi-metal. So graphite is a semi-metal. That's important. Accordingly, it is instructive to examine the known optical characteristics of graphite. In the visible range, graphite appears black. To some extent, these characteristics are reported to be shared by very dense hydrogen. One possible choice for the structure of dense hydrogen consistent with hexagonal symmetry is actually a graphite-like arrangement. So he wrote that in 1991. And actually, well, I'll keep it to myself, but Neil has thought about the sun, but not published about the sun, but that maybe the sun could be metallic hydrogen. So it's important that dense hydrogen and a graphite-like lattice has now been achieved on Earth. That was done in 2013. The spectral signature of a strongly interacting hydrogen molecule is consistent with the presence of graphene-like sheets, a configuration predicted in early calculations on dense hydrogen. So now we have made graphene-like sheets, which is like a single sheet from the graphite plane, that has now been made in the laboratory. So that's extremely important. We're getting there. Now, if you look at the sun, you see limb darkening, and I've tried to explain this to people. Why is the sun darker on the periphery than in the center? For the gas models, they tell us, well, we're seeing deeper in the center. So we're seeing deeper, so it's brighter because we go to higher temperatures, so it appears brighter. But actually, in order to explain this, you just have to remember that objects that are not too highly metallic, their emissivity will drop as a function of viewing angle. So the emissivity drops, and that's why you get this appearance. And this is outlined in my paper, in my papers. And I've talked about this, sunspots. They're a manifestation of lattice structure and directional spectral emissivity, not lowered temperature. So the fact that a sunspot appears black at the center is because it's more metallic there, and its normal emissivity is lower. It's not a temperature effect. And if you look at granules, they have the same behavior. Now, granules are throughout the solar surface, and they have the same behavior as limb darkening. You know, when you look at the intergranule lanes, they look dark. So the granules are like little bumps on the sun, and so when you're viewing them at an angle, see, it looks dark. So this is confirming that you have the same material, of course. It's over the whole sun, and the granules are displaying the same emissivity characteristics. So lower emissivity with angle. So this is consistent. So when you try to use this as a means of explaining limb darkening, sunspots, granules, and faculae, this simple plot can explain all of it. That if you have a non-conductor, so if you have the photosphere is not highly conductive. It's more like a non-conductor, but it's not an insulator, but it's more like a non-conductor. So it's got high normal emissivity, okay, and then the emissivity drops as you increase the viewing angle. So if you're looking at it like this, straight down, let's say I look straight down on the floor, that's normal, and then if I increase the viewing angle, the emissivity will drop. But in a metal, you see, in a metal, when you're on the normal, the emissivities are low, and then the emissivity increases as the angle increases, okay? Now, what's interesting about that is that if you look at old reports of sunspots, people actually wrote that the sunspot appeared to be brightening as it moved towards the limb. Now today, in order to explain that, what they say is, well, what you're seeing is a contamination from the photosphere. The photosphere is causing the sunspot to look like it's becoming brighter, okay? So there's always an alternative explanation. But in the condensed model, the sunspot would be expected to maybe brighten a little bit as it moved towards the limb. So I've said that the photosphere is comprised of metallic hydrogen, which has assumed a graphite-like layered hexagonal lattice, which I call type 1. The internuclear distances within the lattice are such that the material is a semi-metal. It's not highly conductive. Sunspots, faculae, and the convection zone are comprised, so that's lower in the sun. The convection zone is lower in the sun. Are comprised of metallic hydrogen, which has adapted a graphite-like layered hexagonal lattice, which is type 2. However, in this case, the internuclear distances is decreased, such that the materials become highly conductive and able to support strong magnetic fields and the solar dynamo. So what I'm saying is that, let's say I'm looking at the hexagonal distance between the hydrogens. Let's say it's this big, let's say in the photosphere, and all it takes to make it more conductive is just to shrink it a little bit. It'll become more conductive, and that's what's happening in a sunspot. So you have the same general structure, you just lower the interatomic distance. The solar core is likely to be metallic hydrogen, which has adopted a body-centered cubic. That was first proposed by Professor Setsuo Ishimaru. And so what he's saying, I'm saying now there's going to be a different structure in the core. Now, when Ishimaru proposed this, he was thinking that all the mass of the sun was in the core, just like in the gas models. Now, in the metallic hydrogen model, remember, the mass is fairly evenly distributed in the sun, okay? Because it's mostly a liquid, and in the sun, in the center of the sun, you have solid body rotation for the core. That's known that it experiences solid body rotation. So that's where now I change the phase, and I think Ishimuru's choice is fine, okay? But I don't have the same densities that he has. He still says the core is like at 150 grams per centimeter squared and cubed, and I say no, it's still more like 1, close to 1, just slightly more than the photosphere. Now, it's important, in the corona, we possess both free atoms and ions, and sparse distribution of metallic hydrogen of type 1, which is like the photosphere, which has been ejected into the solar atmosphere from the body of the sun. The chromosphere possesses both free atoms and ions, and sparse distribution of dense hydrogen, which is molecular in nature. So in the chromosphere, when you see chromospheric material, I'm not saying chromospheric material is metallic hydrogen. That is just dense hydrogen, and it results from condensation reactions in this region. And the transition zone does not exist, so that's a big difference. In the gas model, they have to come up with a transition zone to explain certain elements, and I don't use that zone. So does the sun have the real surface or not? I mean, it's without question. And people have been saying the sun has had a real surface throughout the centuries. Even when the gas models were there, the observational astronomers were still writing, the sun has a real surface. Now, Zirin, and I loved reading his book. He was a very honest scientist, I think. He has a beautiful name, Captain Corona. He studied the corona, and they nicknamed him Captain Corona. He's deceased today. But he was a very honest scientist. I loved reading his work because he was very transparent in his writing. Years ago, so this is an example of what he wrote, years ago journals were filled with discussions of the height of the chromosphere. It was clear that the apparent scale height of 1,000 kilometers far exceeded that of hydrostatic equilibrium, which we got from theory, right? In modern times, a convenient solution has been found: denial. Although anyone can measure its height with a ruler and find it extending to 5,000 kilometers, most publications state that it becomes a corona 2,000 kilometers above the surface. We cannot explain the great height or the erroneous models. While models say 2,000, the data says 5,000. And of course, some of the lines and the spicules, they extend to 20,000 kilometers, okay, much, much higher. So they can't support the chromosphere, so you have to have a means of supporting this. But for them, the sun doesn't have a real surface, so how do you support this layer, the chromospheric layer? They don't have a real surface under it, so there's nothing to support it. Now remember that the atmosphere of the Earth is supported in part because, you know, the Earth is condensed matter. So if an atom comes and it travels towards the Earth, it's going to bounce off the Earth and then help to support the atmosphere. You can't do that in the sun because you have a gas. So chromospheric extent, what's nice in the condensed matter model is, of course, I have a real surface, so I get to support the chromosphere very easily. The continuous spectrum of the chromosphere also has a continuous spectrum, and it constitutes direct evidence that this region of the sun contains condensed matter. The chromosphere is a site of hydrogen recapture and condensation in the solar atmosphere, and that's evidenced by emission spectra. The chromosphere therefore acts to help conserve the mass of the sun, harvesting hydrogen atoms and protons which have been released into the atmosphere. So this is an example from Erdl, and what Erdl, he's a Nobel Prize winner, I think he's a chemist by training, but he wrote this paper, and what he did was he took silver clusters, so M there could be Ag, okay? And it was a silver cluster, it had a certain mass, and another silver cluster combined with it, so the two made a big cluster, and then there was a little star there that the cluster was not relaxed, it was an activated state, and then what happened was that one of the silver atoms left the silver cluster, and it was activated, and now you had a relaxed silver cluster. And then to deactivate the silver atom, you emit light. So when you have condensation reactions, you can get light emission. That's the lesson of Erdl. And that's a powerful lesson for the sun. Why? Because in the chromosphere, what do we have? We have emission lines, right? So when you look at the solar spectrum, the continuous spectrum, we have Fraunhofer lines. Those are absorption lines, right? But in the chromosphere, we have emission lines. Why do you get emission lines? When you have a process where you have a condensation reaction and you don't have an adiabatic path out for the heat. So you don't have a way to channel the heat out, like let's say condensation on a leaf, right? Water condenses on the leaf, and most of the heat is going to leave through the little leaf, right? But in the sun, in the chromosphere, you don't have that mechanism. You don't have a means for the heat to leave. Now, condensation reactions require a means to get the heat out. So what do? We emit light. So the fact that you have light emission is a nice sign that the chromosphere is experiencing a condensation reaction. That's what's going on there. That's why we have the emission lines. So here's an example. You could take some hydrogen clusters. You can bring them together. You'll get you'll get a hydrogen, an excited hydrogen atom, and that will come and emit a photon. And in the chromosphere, not only do we get the Balmer series and the Lyman series, you know, we get the other series as well, the distance series. So you get a whole bunch of hydrogen emission lines in the chromosphere. Well, how do you explain all these lines? Well, the nicest way is by remembering that in condensation reactions, you're going to get emission lines. Here's an example. Now, this is important. So I'll start with the bottom of the slide. It's known that magnesium hydride exists both on the disk and in sunspots. And there's a whole bunch of other hydrides on the sun. Calcium hydride, there's methylene, there's hydroxyl, water, NH, SH. So all these compounds exist on the sun. So there's a whole bunch of hydrides on the sun. But what's interesting, calcium hydride and magnesium hydride have been known to be present since the beginning of the 20th century. So for a long time, we've known that they're there. Now, if the sun is so hot, why are we getting these molecules there, right? We're supposed to be in the 5,000 degrees range here, like we're above the photosphere. Why are we getting molecules? Well, the reason we're getting molecules is because these molecules are working to harvest hydrogen. So we have these free atoms, like magnesium hydride, magnesium, which grabs a hydrogen atom, and then it'll deposit that hydrogen atom on a cluster. So we have a condensed structure, and the magnesium hydride will deposit it on that cluster. The magnesium will come off as magnesium plus in activated state, and then that will release a photon. Now, all the chemists in here know that magnesium doesn't like to be magnesium plus. It really likes to be magnesium plus 2. Same with calcium, it likes to be plus 2. So why do we have so much calcium plus and calcium plus 2? So when they talk in the sun, these leads to calcium 2 emissions. Okay, the same reactions with calcium leads to calcium 2. But calcium 2, that's a spectroscopic nomenclature for calcium in the plus 1 state. Calcium 2 is calcium in the plus 1 state, not plus 2 state. Okay, so why is it that it's calcium in the plus 1 state in the chromosphere, not plus 2? So there's a lot of plus one hydrogen calcium, and that's because of these reactions. Calcium is contributing to the deposition of hydrogen in the chromosphere. Now, an interesting one, actually, I love this one. This is actually reactions of helium hydride. Most people don't realize that helium can actually make molecules. And the helium hydride cation there in the upper left, so you have helium, hydrogen with a little plus sign. That's helium hydride cation. That's been made in the laboratory. So whenever you have helium and hydrogen mixed together, you always get these helium hydrides. Either molecular helium hydride in activated form, which you see in the lower part there. On the lower left, you see HEH with a little star. That's helium hydride that's in activated form. Or helium hydride cations. These are known to exist in mixtures of hydrogen and helium. And I'll show you pictures later. We got lots of helium around the sun, especially when it's active. So we got a lot of hydrogen, we got a lot of helium, so we can make probably helium hydride. And so helium is interesting because we have helium triplet emissions on the sun, and people can't understand why we have so much buildup of helium triplet on the sun. And these types of reactions actually explain why we get triplet helium on the sun. So you take helium hydride, cation, you condense it with a condensed hydrogen structure in the chromosphere, so like a spicule, and then you get a complex. Then the helium plus can be ejected in activated form, and then you get the helium 2 emission lines. All the helium 2 emission lines can be explained that way. Now, or you can actually just emit, the charge can stay with the complex, and then you produce activated helium, and then that's an orthopath. Now you got the 2 electrons in helium, and one of the electrons has been activated, and once you do that, you can combine that helium with hydrogen again, and now it enters this second cycle at the bottom, and this is how you get the triplet. So this explains why you get such important helium triplet lines in the sun, and that's very hard to explain for gas models, because in order for them to get these kinds of lines, they have to invoke that photons are coming from above in the corona and coming down and exciting the helium that's sitting in the chromosphere. So they have to They have to pray that we got some photons here magically are going to come and excite this helium to give us these helium triplet lines. What I'm saying is we're getting helium triplet lines because we're seeing an emission that's a resultant of condensation of helium hydride activated molecules in the sun. So this is a completely new way of looking at the chromosphere. So the corona is divided, currently it's divided into three. There's the K corona, the F corona, and the T corona. So these three coronas, even if they have different spectra, are actually manifestation of the same structure. So this is completely different than the gas model. I'm saying there is only one corona here. Now, why do they have different spectra? Well, the continuous spectrum of the K corona does not represent photospheric light scattered by relativistic electrons. That's what they're telling us it is. Together with the F and T corona, it constitutes direct evidence that the corona itself is self-luminous condensed matter and becomes increasingly cool. The K corona, the region of the corona nearest to the sun, is warmer, and therefore it's incandescent. So it's closer to the sun. Now we're just going to think about the rod in the I have built a forge for my son Luke. You know the guy in Scotland? Years ago I built him a forge. Now if you have a forge, you take your piece of metal, you put it in the forge, it's going to get red at the tip where the heat is, right? But you can still hold it at the other end. So it's incandescent at one end, but it's not at the other end. And that's the same thing in the corona. What happens is you have one structure, when it's close to the sun, that's the K corona. It's incandescent there, it's hot. But as it cools down, then it becomes the F corona. So the K corona emits a continuous spectrum like the photospheric spectrum, indicating that the two share a lattice structure. The K corona is devoid of Fraunhofer lines because the region of the sun there is no longer has enough density of free atoms to absorb the light. It's just above the photosphere. So remember, in the photosphere, why do you have Fraunhofer lines? Because you have the photospheric surface, and then above the photosphere, you have free atoms over here, and they can absorb that light. They're cooler, and one of Kirchhoff's law, which is correct, that law is correct, that these cooler atoms can absorb the light, and therefore, when we see the solar spectrum, we see an absence of light at certain frequencies. Those are the Fraunhofer lines, right? But in the corona, we're above the level where these atoms can absorb. There are not as many of them there. So the corona is just emitting the spectrum, and that's why you don't see the Fraunhofer lines. And so it's not that relativistic atoms went over here and scattered the light. That's not what's happening, okay? The corona is devoid of Fraunhofer lines because this region of the sun, okay, I just said that, is higher. As the elevation above the photosphere increases, the corona cools, and it slowly loses its incandescence. Its reflectivity becomes more dominant over its emissivity. So now it's reflecting the light. So now what is it doing? Now it is reflecting the solar light. It's reflecting the light of the photosphere because it's cooled down. Now it's becoming reflective. So the F corona is not produced by interplanetary dust resembling graphite, which, by the way, notice how graphite is coming back in here. These Japanese guys, Mr. Mukai, he proposed, and his collaborators proposed in 1974 that this dust that we need should look like graphite. Well, what it is it's actually just photospheric material that's now so far away from the photosphere, it's cooled down, and now it's just reflecting the light, and since it's photospheric in nature, it looks like graphite. It behaves like graphite, okay? So it's just cooled down. So the F corona is not interplanetary dust. It's actually solar material. The presence of highly ionized species in the corona, like iron-25, is associated not with temperatures in the millions of degrees, because we know that the coronal spectrum is reddening as we move away from the surface, but rather with the presence of condensed matter in the corona, which possesses an elevated electron affinity. So when you have condensed matter, you can pull electrons towards you and therefore strips atoms and ions of their valence electron. The corona is a site of electron recapture and helps to maintain the solar body neutrality. So here's an example. You have metallic hydrogen in the corona, and there's an iron atom, and it's going to touch the metallic hydrogen. All of a sudden, it gets activated. It gets stripped of its electrons. A certain number of electrons are going to stay with the metallic hydrogen, and iron is kicked off. Now you've got this. In one step, I can pull all the atoms, all the electrons away, except 1 or 2, and now iron emits light from that 1 electron. Okay? You have to have at least 1 stay. Why? Because it's a condensation reaction again. You're pulling the electrons away, so we have to have a way of getting rid of that heat, and that's where the light is produced. So that's why you, not only are you seeing these species, but they're emitting light. That's another thing that's happening. So electron affinity, not elevated temperatures, account for the production and emission of species like iron-25 in the corona. The species is produced in 1 step. So in the gaseous model, of course, you need 25 steps or 24 steps to produce this. But here it's done in 1 shot. Now also, I've written about the solar winds and solar activity. So what is happening in the sun with solar activity? And this is a helium-2 line. So now this is helium that's lost 1 electron. And it's giving us an emission line. And so what you see is when at the back pictures of the sun, the further ones from you in 96 and 2006, you can see that there's not much helium there. The sun is quiet. But as the sun is active, there's a lot of helium around it. So what's happening? So what we're saying is the sun is made up of metallic hydrogen layers. It's got layers of hydrogen in it. It wants to have only hydrogen in those layers. Any other element becomes tied in intercalate planes. So here's, now you see again the hydrogen configuration, and now you start putting, if you're a non-hydrogen atom, you don't get to be in that plane. You get to be between the plane. Well, it's known, this is known to occur in graphite. So again, we go back to graphite chemistry, and we see that in graphite chemistry, we have atoms that could be in the intercalate region. That's why graphite is used as chemical absorbers, right? We have charcoal masks. That's why we use them. So we can grab these species and they get trapped in their intercalate regions. So what is happening in the sun? The sun is synthesizing all these nuclei, not just helium, everything. The sun can make all the elements, okay? It's only the gas models that are insisting that it can only make helium, basically, essentially only helium. In the condensed matter model, it can make all the elements, and we see all the elements there. Now remember that in the gas models, in order to have all the elements, they weren't made in the sun. The elements had to be made in first generation stars, which exploded, and now that they've exploded, these elements are now around us. Talk about a complicated model. Stars that no longer exist produced all these elements. Let's just stick with our own sun. If we can make these elements on Earth, why can't our sun do it? So it seems to us that, it seems to me that the simplest way is to say the sun can make all the elements, okay? And that's also the answer for the neutrino problem. People have tried to say now neutrinos are changing their type on the way to the Earth. Let's just say we didn't understand the reactions in the sun, and that's why our neutrino counts aren't right. Not that we're changing neutrino types on the way to the Earth. So here now what we have is we have planar metallic hydrogen. In it, we'll have intercalate regions. So if you're not a hydrogen atom, you get out of the plane. You can't belong in the plane. The plane has no means of binding with you. So it kicks you out and puts you in the intercalate region, just like graphite does. Of course, graphite's not synthesizing elements. Now what can happen here is, and this is known in graphite, you can have intercalate regions that get populated like this. Let's say you have 10 layers of hydrogen, and all of a sudden you have an intercalate region. Now what can happen in graphite is all of a sudden this intercalate region, it's condensed matter. But all of a sudden it decides to go into the gas phase. And what happens is that the graphite just blows up and it expands 100-fold in the laboratory. Okay? So that's important. Why? Because look, how would we create a giant? Well, let's have our intercalate regions and let's just put intercalate atoms between each of these layers. Now stellar expansion just occurs because what happens? The intercalate region goes from condensed matter to gas. So you get a giant produced. So that's why you can have G1, you can have G-class giants. So the sun is a G-class star, and if it went to a giant, it would be a G-class giant because it's a G-class star currently. Okay? So this is a completely different way of looking at the evolution of the stars, because intercalate atoms can undergo phase changes from solid to or liquid to gaseous. This helps account for the fact that G-class stars can range from dwarfs to supergiant. It's not related to the nuclear fuel being consumed, which is, now in the gas model, what they have to say is in order to get these structures, now you've got, okay, at first we make hydrogen, and then the core collapses, and now we make helium, and then we have expansion, and it's, you know, everything has to be done with nuclear reactions. There's no change in phase here. Whereas I'm saying it's a change in phase that causes these stars to explode. Look at a supernova. Again, imagine that in the blue circle here, in the star on the left, okay, all the intercalate atoms are in this region, in the little blue region. And all of a sudden, it just explodes. So now you'll get a supernova, just by a phase change, okay? Now, how are they trying to explain to us supernovas now? Well, unfortunately, you'll find papers published in the last year that dark matter or black holes are producing supernova. Let's just stick to a phase change. Now, I want to close with the words of George Ellery Hale, because a lot of people give amateurs a hard time, or people that weren't formally trained in astronomy. They try to say, well, you don't belong in astronomy because you weren't formally trained in astronomy, okay? But science doesn't work that way. When God created us, and when we were made, there was no division between the sciences, you know, biology, physics, chemistry. There was no division. We made the divisions, okay? So when we look at science, a scientist is allowed to look at everything. You can't say, well, now I'm only this kind of scientist, so I can only look at that. That's a very dangerous thing. People should, and especially engineers, should start looking at what scientists are doing. Because the engineers need to make things work, and they'll start realizing that, you know what, this is just not working here, okay? So I love engineers because they make things work. So this is the quote from Hale. Of course, he's the discoverer of magnetic fields and sunspots. He's one of the co-founders of the Astrophysical Journal. And this is what he wrote on the death of Huygens, which was, he was an amateur astronomer. And when he died, this is the tribute that he wrote to him. If it be true that modern observatories with their expensive equipment tend to discourage the serious amateur, then it may be doubted whether the best use is being made of the funds they represent. For the history of science teaches that original ideas and new methods, as well as great discoveries resulting from the patient accumulation of observation, frequently comes from the amateur. To hinder his work in any serious way might conceivably do a greater injury than a large observatory could make good. So if you hinder the astronomer, you can hinder some guy who's got an idea, and you could build all the observatories in the world, but you won't get that idea back. The surest message and the strongest appeal will be to the amateur, who with limited instrumental means, and to the man, however situated, would break new ground. I'd like to acknowledge my son and the other people who collaborated in this talk, and especially my wife, Patty. And if people knew my wife, they would know how blessed I've been in life. So God bless you all, and thank you very much for your attention.